Okay, so am I audible and can you see my screen?
So you are audible, but we can't see your screen.
One second. Is it visible now?
Yes, all set.
Okay, okay, fine. So yeah, so I was recalling the notation. So we denote our data stream by this symbol row, which has element A1 to AM, and we call these elements as token. And each token is drawn from certain universe. And we assume that this is one number, a number from 1 to n. Yes. So you can think of the elements in the data stream are numbers from 1 to n. That is this AI belongs to n. So basically there are two parameters. One is stream length and the second one is size of universe. So stream length is m and size of universe is n. Okay, so so for example, say if n is equal to 5, one data stream could be say 1, 2, 1, 1, 3, 5, 4, and so on. And these we call as token. Okay, so I hope the notations are clear. Okay, so now we'll see, we recall the problem of frequency estimation. So via count sketch. Okay. So suppose our universe is, for example, uh, universe of alphabets. Suppose our data stream is like this: B A B A B B and so on. Right? So our input will be like the stream of alphabet, and our aim is to basically summarize this stream of alphabet in a very small size sketch, such that using that sketch we should be able to correctly estimate uh, frequency of a given query item. Okay. So so is the problem setup clear? We saw the same problem like in our previous class as well. Okay. So so we'll just quickly recall our previous our earlier algorithm, which is count sketch. Count means sketch. Sorry. So can you recall what was the count sketch algorithm? And Okay, so in count sketch algorithm, we use one hash function, universal hash function, that takes the element from the universe and map it to one of these bins. So suppose this bin size is k. So which is from okay. So basically, what it does is map each element from of the universe to one of these k bins uniformly at random. Okay. So okay. So suppose, for example, H maps A2, for example, in second position, H maps B2, maybe third bin, C2 first bin, maps D2 second bin. Okay. Okay, so I'll just rewrite this here: A B A A B B C C D E G. Okay, so A is mapped to second bin. So here what we'll do, so initially all the bins were zero,
Zeros.
initialized with 0. Yeah. Any questions? Okay. So once we process this element of the stream, we'll add +1 in this bin. B maps to this third bin. So this will add up +1 over here. And these two A's will again go to this bin, and it will add +2 over here. And then these two will go to this bin and they will add +2 over here. C maps to first bin. So these two will go over here. And they will add +2. D goes to second bin. So this will add +1. E goes to which bin? Fifth bin. +1. F goes to fifth bin. +1. And G goes to fourth bin. This is +1. So overall, the sketch will look like this. So this is 2, 2, 3, 4, 3, 1. 1 and 2, right? And so suppose if we need to estimate frequency of, suppose our query item is A. So what will be the estimate of frequency of A? So basically we'll see in which bucket A is going. So it's going in the second bucket. So we'll query item A. So we'll report frequency of A as 4, right? And of course, we repeat it several times. And suppose we are repeating it at A times, we'll get T estimates and we'll report minimum of all the estimates, right? Okay, so this was count min sketch algorithm. So one limitation of count min sketch algorithm was that it kind of gives an overestimation. Basically, whatever is the actual frequency of A, the frequency estimated by the count min sketch is greater than the actual one. And the reason is basically it can be possible that some other elements map to the same bucket in which the query item has been mapped. So their count will also be added in the frequency of query item, right? Okay, so this count sketch algorithm in a way address this by introducing one more hash functions. Okay, so any doubt on this count means sketch algorithm? So although we have covered it last time. Okay, so now we'll see count sketch algorithm on the same example. Okay, so suppose we have the same example. We'll have A, B, A, A, B, B, T, E, F, G. Okay, so in count sketch algorithm, we have one hash function like h, which maps the elements, the tokens to one of these bins uniformly at random. But on top of that, we'll have one more hash functions, which decides whether we should add its value or whether we should subtract its value, right? So what I mean, it will be clear in a minute. So basically we have another hash function, say G, that maps element of universe to either -1 or +1 with probability half. Okay. So suppose G of A is say +1, G of B is say +1, G of C is say -1, G of D is say -1, G of E is say +1, G of F is say +1, and G of G is say +1. Okay. So suppose our sketch size is 5 as before.
So one quick question: how did you decide that +1 and -1 for G's?
Yeah, so this is, yeah, so the motivation of using G is so that our estimate could become unbiased. So our count means sketch algorithm gives overestimate. So we want basically the random variable which estimate the frequency of the query item. Its expected value is same as the ground truth. So that's why we use G. And once we see the analysis, maybe I'll be able to answer your questions. So it somehow kind of average out the overestimation part.
Okay.
Okay, so it will be more clear once we see the analysis. So right now I'm just presenting the algorithm. So, okay. So again, so G of A is +1 and it maps to the second bin, right? H of A is 2. So all these A will map to second bin, and the value will be +1 into their frequency. So basically we'll add +1, +1, and +1, right? B maps to third bin. So B maps over here, and G of B is +1. So we'll add +1 over here. So these we have already taken care of. These two will again go over here and we'll add +2 for them. C goes to first bin, but G of C is -1. So their contribution in this bin will be -1 for each of these, right? D goes to second bin, and G of D is -1, so its contribution is -1. E goes to fifth bin, and its contribution is +1, so it is +1. F goes to fifth bin again, and its contribution is +1, so it is +1. And G goes to fourth bin, and its contribution is +1, so it is +1. So our resultant sketch will look like this. Yeah, is there any question? C minus C -1. So these will be -2. This is -2, and this is +3 -1, 2. This is +1 +2, 3. This is 1. This is 2. Right? So suppose our query item is A. And suppose we denote this sketch as CS. So then we report frequency of A as basically G of A, whatever the sign that query item has, into, again, we'll go to the same position in which A is mapped. So basically we'll go in the same bin in which A is mapped. So A is mapped in this bin, and G of A is +1. So we'll report the frequency as +1 into 2, and this will be 2. Right, so I'll just take a pause and let me know if you have any question on the algorithm at least. Right, so we are doing that. Yeah, go ahead.
Here we are
Yes, sir.
underestimating right now. I mean, it will be like A is 3, we're getting answer as 2.
Yes, A is frequency of A is 3. Yes. So actual ground truth is 3, and we are outputting it as 2. Whereas here we were outputting it as 4.
Sir, could you just repeat this computation G of A into CL count sketch of H of A, that computation?
Okay.
Was in...
So basically here we use two hash function. The hash function H decides in which bucket that item is mapped. So basically in which buckets the contribution will be added, and G decided whether its contribution will be in positive side or negative side. Okay, so suppose we need to see what is the contribution of this element A. So H of A is 2. So basically it is mapped in this bucket. So we need to add one over here, 1 here, but its contribution will be basically its frequency times G of A, right? So we'll add +1 over here. And suppose we need to see what is the contribution of B. So H of B is 3. So it is mapped to this bin, and G of B is +1. So we'll add +1 over here. And again, we get these two A's. They are mapped to second bin. So correspondingly, we'll add +1 over here. Suppose, yeah, so now suppose we want to see the contribution of C. So C is mapped to the first bin. So contribution will be added to this bin, but G of C is -1, right? So we'll add the frequency of C into G of C. So the result will be -2, -1 and -1. So the overall contribution is -2. right?
Okay,
So
sir.
Yeah.
I have a doubt on count main sketch algorithm. So
Yes.
basically there we are using multiple hash functions, right?
Yes, yes,
You
yes,
have
yes.
shown here only one,
Yes,
but
yes.
typically
For
we
one.
use multiple.
Yeah, yeah, yeah.
So when we use multiple hash function, there also you think it will be maximum always? The frequency of A will be always maximum?
No, I'm not saying maximum. So what I
What I mean to say is like not maximum, sorry. It will be more than the actual result.
yeah. So suppose my claim is, suppose our estimated frequency is, say, suppose I'm denoting it by f of a hat, and suppose f of a is ground truth frequency. So this will be at most f a.
Yeah, got it. Yeah, it will be yeah. So it cannot be lesser than that.
It cannot be
Okay.
less than.
And here in count sketch also you are saying like we will
No,
be
sorry,
also
sorry.
adding.
One second. So I made a mistake. So it is estimated frequency will be this. This should be at least the ground truth frequency. So this is
Yeah.
this is ground truth. Yeah,
Correct.
go ahead.
So in count sketch, so there also we are having multiple hash functions itself, right?
Yes,
Like
yes.
as you have shown. So
Yes.
so how many is there any limit of like how many hash function we can have?
Yes,
Like
yes. So yes, we'll see that in analysis. So right now I'm just explaining the algorithm by one example. We'll do the analysis here.
okay, got it.
Any more question on this algorithm? So roughly you can think of count sketch algorithm is count means sketch plus one sign function. And that's all. Okay. So now we'll just try to analyze this count sketch algorithm. So basically we'll first define what is its estimator and calculate its expected value variance, and we'll show the concentration. So
So one question.
yeah, sure.
So in order to decide this g of A is +1, g of C, so is it purely random or like how we have decided this hash function, whether it will be +1 or like, so I understand like it is based on that hash G only, but
Yes.
It can be random, right? Like this might impact our result also.
Yes. So basically, you can think of the functionality of G is as if for each item it toss a coin, and based on the whether it is head or tail, it assigns the value either +1 or -1. Right, and it can be implemented using two universal hash functions. Like, so suppose I think last time we saw example of universal hash function. So can use AX plus B mod P, and we used mod, I think, K. So here if we choose K as 2, so we'll get where A and B are randomly sampled from our universe. Right. So you can design, I should write this as G. You can use this type of function, and this will do the job for us. Right, so these are universal hash functions. So basically the output of this function will be either 0 or 1, but we can decide if its output is 0, we can use it as -1, and if its output is 1, you can use it as +1. right?
Okay.
Okay. So now we'll just try to analyze our algorithm. So okay, so suppose let A be our query item. Okay. Then for each item I, so first we'll just try to see how we can write our estimation in mathematical form, right? In form of random variable, in which is function of h and g and the elements of data stream, and then we'll try to calculate its expected value and variance, right? Then for each item, say j in n. So I use this indicator random variable yj, which takes value 1 and 0 if h of j is h of a and h of j is not equal to h of a. So basically it takes value 1 if jth element is also mapped to the same bin in which the element a has been mapped, right? So it means that item j contribute to, basically this is the location in which the ith item, our query item, has been mapped. And suppose I'm using this array type notation, so I'm denoting this array as CS. And suppose we need to fetch, say, some position, some index, so we'll just use it like this array type notation. So it's item j contribute to this cell in which a has been mapped if and only if h of j is equal to h of a, right? That is yj is equal to 1, right? So is there any doubt on this statement which I'm making here? Right, so for example, in this case, so A is our query item, so it maps in this bucket, and which other elements map to, and D is also mapped in the same bucket. So so basically h of D is also 2. So the frequency, so basically D will make some changes in the bin in which A has been mapped. So that's what I'm writing over here, right? So if h of j is equal to h of A, then basically that item j will contribute to the same bin in which our query item has been mapped. And what will be the contribution? Yes, so what will be the contribution? So here, what is the contribution of D? So here D is contributing -1. Why -1? Because G of D is -1, right? So basically the frequency of that item into G, basically the output of that function G corresponding to that element J, right? And the amount of contribution will be frequency of item J into G of J. Is this clear to everyone? Okay, so I'll just repeat it once more. So basically some other item J contribute to the bin in which our query item has been mapped. It will contribute only if h of j is equal to h of a. Basically, it is mapped in the same bin in which our query item a has been mapped. That is yj is equal to 1, and the amount of contribution will be basically the frequency of that item j into g of j. Basically, whether it is adding in that its frequency is getting added in that bin, or its frequency is subtracting from that bin, right? So that's how we'll see the contribution of some other element j which is not equal to a. Okay. Okay, so now we'll try to write the estimator, our estimator of frequency of query item A. Okay, so suppose I'm denoting that estimator as say, x. So what will be x? Any idea?
Kind of an expectation. No.
Your voice is a bit low.
Is it expectation of summation of y of j?
So right now we we want to write our estimator in form of random variable. We'll take its expectation later on. So essentially it is CS of h of a into g of a. Basically we'll see in which bucket a has been mapped. We'll take out its entry and multiply it by g of a. So this is what we did over here. Right? So we report the frequency of a as g of a into CS of ha. Right? So this is what we'll try to do over here as well. This is g of a, but now how to write this term mathematically? Okay, so
That identity, that I operator,
okay,
I don't know. I don't know
Okay,
what is
so-
that called as. Yeah.
okay. So first I'll write this indicator random variable yj. Okay, so yj takes value 1 if h of j is equal to h of a and 0 otherwise. Right. So it will take care of basically it will add up the contribution of only those entries which mapped into the same bucket in which A has been mapped. Okay, and their contribution will be what? Basically their frequency times their sign value. Right? And this will add up for all the element in the universe. Right? So let me repeat it again. So our estimated frequency is basically the sum. Sorry. Okay, so our estimated frequency is basically sign of that query item, basically G value of that query item into will probe in the cell in which item A has been mapped, and we'll just fetch out the entry and multiply it by G of A. So this is what something similar we want to do. So this is G of A. So we'll multiply G of A anyway. And somehow we need to mathematically write this term CS of HA, right? So we'll take help of this indicator random variable yj. Okay, so yj takes value 1 when h of j is equal to h of a. So we'll write yj, and it will be 0 for all those j which are not equal to, for which h of j is not equal to h of a. Right. So the contribution of jth element will be its frequency times g of j, and we'll sum up for all the elements in the universe. Right. So this is somehow, this term is analogous to this term.
Can you please explain it once again? I did not understand that into y of j, why it is coming.
Okay, so basically, what is the value that are there in CS of HA? Of course, the frequency of query item A, and there'll be some other elements which mapped in the same bucket in which A has been mapped, right?
Correct.
Right. So their contribution we are capturing by this random variable yj. So note that this random variable yj takes value 1 if h of j is equal to h of a. So any other query, any other element in the stream which is mapping in the same bin in which item A has been mapped, so their contribution will be added. But for the others for which h of j is not equal to h of a, it will be 0. Yeah. So their contribution will not be added, right? So all those elements which mapped in the same bucket in which A has been mapped, so their contribution will be added, and that will be taken care of this random variable yj. But now what are their contribution is the way we had designed our sketch function is their frequency. Fj denote the frequency of the jth item times the corresponding sign value, right? So their contribution is Fj into Gj into Yj, and we'll add up for all the elements in the universe. And for all those elements for which are not mapped in the same bin in which A has been mapped, the corresponding Yj value will be 0. So those will be taken care of by this indicator random variable Yj. Right. So this is slightly subtle, but yeah.
Okay. Sir, why is there a G of A outside again when you have a G of J within the summation?
Yes. So this is how we design our algorithm. Right. So suppose, for example, if you need to query the frequency of item C, so it mapped to this bucket, and the value is -2, right? So that's why we are multiplying it with G function again, so that its negative effect can taken care of in some sense, right? So the frequency of C will be G of C -1 into the value, corresponding value -2. So the reported frequency will report the frequency as 2. So you can think of this as our part of our algorithm to take care of, basically, while hashing, we are multiplying it by function G. So while retrieving, we are just trying to compensate it in a way.
Yes, thanks. Got it.
Okay.
Sir?
Yeah.
Sir, here if you have to report the frequency of D, then it will be negative, right?
And D is negative, why it is negative? What is H of D? No, yeah, so D will be negative, right? You are right. So in this case, it will be negative. Okay. So note that in case of count mean sketch, whatever we are reporting, it's non-negative, will be at least 0. But in case of in case of count mean sketch, whatever we are reporting, it's non-negative. But in case of count sketch, it can be negative as well. Okay. So now we'll just try to compute the expected value and variance of this random variable X. Okay. So everyone with me? At least say yes or no.
Yes, sir.
Okay, fine. Thank you. Okay, so this summation, inside summation, is for all the elements in the universe. Okay, so we'll just split the summation in two parts. So basically one with A and one without A. Okay, so this is GA, and this is F of A into G of A into Y of A plus right? So I just took one term over here and the remaining n minus a terms are sitting over here in the remaining summation. Okay. So here we have this GA square, right? So GA into GA, it's GA square. What is the value of GA square?
1.
1, because GA can take value either +1 or -1. So this value will be 1. What is the value of YA? So note that Yj takes value 1 if h of j is equal to h of a. So Ya will be 1 always, right? So because h of a is always equal to h of a. So this is 1, right? So we left with Fa plus this term. Okay. Okay, so now we'll try to calculate the expected value of this random variable x. So this expected value of x will be what? So what will be the, if we take the expectation on the right side, what do we get? So this is E of Fa plus G of A sigma okay. So this is constant, right? So this will be Fa plus E of Ga okay. So now we'll do the linearity of expectation, right? So this is, we'll take the expectation inside. So this is Fj is kind of constant, and the randomness is associated with this function Gj and Yj, right? So this f of j will take out, and we'll have E of Gj and Yj, right? And again, since G and H are associated with different hash functions, so H depends on the hash function H, and G depends on the hash function G. So they are anyway independent. So we can just okay. So what is expected value of Yj? So expected of what is the
Half.
expect?
Half.
Sorry,
Half.
why half?
1 by number of, I think 1 by
1 by what?
1 by the length of
Yes, 1 by k.
yeah, 1 by k.
So expected value of Yj is probability that Yj takes value 1, and this will be, since our hash function is universal, so this is 1 by k. Good. So what is E of Gj?
One by two.
Why 1 by 2?
It can take two values, minus
Yes.
1 or 1, and we're looking for one of the values. So
Yes. Okay, so I'll just expand this expectation thing. So it takes value -1 and it takes value +1, right? -1 into probability that Gj is -1 into probability that Gj is equal to +1. So I have just expanded this expectation term over here, right? So it is -1 with, what is the probability that Gj takes value -1? It's half, right? What is the probability that Gj takes value +1? Again, it's half, right? So overall it is 0. Right. So is this part clear?
Yes, sir.
Okay. So basically, I have just expanded this expected value of Gj expression. So the definition of expected value is the value, and what is the probability that our random variable takes that value. It's -1 into probability that Gj takes value -1 plus the value +1 into probability that Gj takes value +1, and we'll get 0. Right. So if we put these two over here, so as this term is 0, so overall the effect of this term will be 0, right? So our E of x is f of a, right? So that's how our estimation is unbiased. So basically, the random variable which estimates the frequency of our the query item, its expected value is equal to the ground truth frequency of that item, right? And now I hope you are getting some intuition why we use this hash function g, right? So because in some sense you can think of this is an error term, right? So this is the actual quantity and this is error term, and because of this g8 because of we are using this hash function g, the expected value of this error term is 0, right? Because E of Gj is 0. right? Am I making sense here? Okay, so please say yes or no. If you want me to repeat, I can repeat. Yeah. So any
Sir,
doubt
but
in the calculation? Yeah.
Sir, but if what basis the G of +1 -1, then I think the intuition will be fully clear. Now, without knowing how we arrived at that +1 and -1 for the G hash function, I think that is what is creating some kind of non-understanding there.
So basically, just to say that like the motivation of introducing G, so that this is the error term, right? So this is our estimator X, and this is FA is the ground truth frequency, and this is the error term, and expected value of error term turning out to be 0 because of this expected value of GJ is 0, right? And why expected value of GJ is 0? Because it takes value +1 or -1 with same probability.
Okay.
Okay. Okay. So now we'll try to calculate the variance of this random variable X. Okay. So this is unbiased estimator. So again, our random variable X is f of A plus summation J Fj Gj Yj G of A, right? Okay, so we'll use the following property of variance. So suppose X is a random variable and A is some constant. So this is constant and this is random variable. So what is variance of X plus A? And what is variance of A into X? Variance of X plus A is variance of X. And variance of A into X is what?
A
variance X.
square.
A square into variance of X. Right? You can just verify these two by just using the definition of variance. Okay, so we'll apply first over here. So this FA is in a way constant, right? So we'll get this variance of G of A okay, so by okay, now we'll apply the second one. So it will be GA square outside into variance of sigma Fj Gj Yj. Okay, and this value is GA square is 1, right? Because GA takes value +1 or -1. Right, so we left with this. Okay. Now we'll just use, so like the subsequent steps are like somewhat calculations, but anyway, we'll do it just for sake of completeness. So variance of X is what? Variance of X is E of X square minus E of X whole square. Okay, so this term is 1. Get, and now is E of Fj, Gj, Yj. Okay. So what is expectation of this term? So just I'll write it over here. So this is the same thing we did in while we calculated the expected value of x. So what will be the expected value of this expression?
0.
0. Why? Because I'll just redo it once more. By linearity of expectation, we'll get minus a, and we'll get expected value of Gj into expected value of Yj. And this is 0 because it takes value +1 or -1 with probability half. Right? So the same thing we did over here. Here, this term. Okay, so this term will vanish. Now we left with this term. So how to proceed further? Okay, so this is basically sigma, like this is something like sigma xi square. So we'll just expand it. So by sigma xi square plus sigma I naught equal to j xi xj. Right, so we'll just apply the same thing over here. This is expected value of sigma fj square, gj square, yj square, j from n minus a. Okay, or maybe I'll just plus use another index, like the same way I'm expanding it over here. J not equal to L, Fj, Fl, Gj, Gl, Yj, Yl. Right. So I've used the same formula over here. Okay. So any doubt on this? Again, this value is 1, right? Gj square is 1, and this Yj square is what? So Yj is indicator random variable. So it takes value 1 or 0, right? So Yj square will be Yj only. Right? So if we take the square of 0, it is 0. If we take square of 1, it is 1. So Yj square is Yj. And then we'll apply the linearity of expectation. So we'll left with here. So this term will be 1, and this will be Yj. So we'll take this fj square outside. This is jn minus a expected value of yj, right? And this will be sigma j not equal to L fj fl expected value of gj gl. I'm just skipping one step over here. Okay, so any doubt on this step? Right, so I've just taken out the expectation inside. So I'll write this expected value of gj, gl, yj, yl. And since g and y are like, they use different hash functions, so they are independent, so we can take their expectation separately. Okay. So now what is the expected value of gj, gl? Any guess?
0.
0, right? Why it is 0?
Because
It will
gj
be
is half minus half, so it's 0.
Okay,
We did it
so
before, right?
yes, so basically this term can take value either +1 or -1, right? So we'll
correct.
just, yes, so I'll just replace it over here, +1, and we'll just inside write down the probability, and then -1, and we'll just write out the probabilities, right? So when it can take value 1, when probability of, basically when gj takes value 1 and gl takes value 1, right? And what is the other case when this value is 1? When both of them takes value -1. gj takes value -1. So because if gj is -1, gl is -1, their product will be +1 again. gj is +-1 and gl is -1. And it takes value -1. What are the possibility? Again, like gj is +1 and gl is -1, and gj is -1 and gl is +1. Okay. What is the probability for this? gj takes value +1, half. This is again half, right? Plus this is again half. This is again half. Similarly, this -1 again will get 1/2, 1/2, plus 1/2, and 1/2. So overall it is 0, right? So that's how basically we used this hash function g, so that this kind of term will get cancelled out and we get unbiased estimator. So this is 0, right? So now we left with this term, and E of yj is what? E of yj is 1/k, right? So it's probability that h of j is equal to h of a, which is 1/k, the scale size. So this is sigma j square by k. So I'll just write this as square minus fa square by k, where f2 square denotes okay. So far our x is our estimator and expected value of x is FA and variance of x is okay. So now we want to which concentration inequality we can apply when we know expected value and variance. We can apply Chebyshev, right? So basically, we now we want to give some guarantees on how concentrated our estimator is with respect to its ground truth value. So just to give that result, we'll use Chebyshev inequality. So Chebyshev inequality says that so if x is a random variable, then probability that x minus e of x is takes more than lambda times this 1 by lambda square. Right. So the same thing will apply on our random variable. Probability of x minus e of x is greater than epsilon times. So we'll use this parameter epsilon 2 square minus fa square as. So basically we are using this term as lambda times variance of x. So essentially, so variance of x is square root of variance of x. We used epsilon times f2 square is fa square. So this is our variance is this much. By root k. So this is epsilon times this get cancelled out. So we get lambda as epsilon into root k. Right. So here we'll get 1 by lambda square, which is 1 by k into epsilon square. And if we choose k as 10 upon epsilon square, so this then we get basically probability of x minus fa is more than epsilon times square minus fa square is at most 1 by 10. Right? So any doubt on this simple calculation? So we just use the fact of expectation and variance of our random variable x, and we applied Chebyshev inequality. Right? So finally, what we don't want, we are not happy with this constant. We want to get this to be sufficiently close to 0. Basically, this should be as close to, this should be at most delta for any delta greater than 0. So for that, we'll apply median trick, right? This. Right.
Any specific reason of choosing k is equal to 10 by epsilon square?
Not necessary. You can take any constant like 100 upon epsilon square. So we'll get 1 by 100. Right. So finally, our aim is to give some epsilon delta approximation kind of thing. Right.
Okay.
So basically we can so this is, in a way, this is error in our accuracy, and this is basically error in our confidence. So we want this to be sufficiently close to 0. So for that, we'll apply this median trick. Okay, so I'll first let me finish this, and then I'll maybe state what is epsilon delta approximation. Then I think we'll be done. So basically, we are not happy with this 1 by 10 or any constant. We want this to be true for any probability delta for any delta greater than 0. Right. So the median trick says that if we repeat okay, so I'll just state, so it says that suppose we have an algorithm A that estimates incorrect range of epsilon. So basically, the error in the estimated value and the ground truth result is not more than epsilon, with say probability 0.9, then we can design a new algorithm. Our new algorithm A star will output in range epsilon with probability 1 minus delta for any delta than 0, and our algorithm is basically repeat A for t times, where t is order log 1 by delta times, and output the median. All t answers. Okay, so this is called median trick. T times independently. Right? So the same thing will apply over here. So we got one estimate and we just repeat it T times, where T is order log 1 upon delta, using different independent hash function H and G. So let me call this equation 1. Yes. So essentially what we are doing, so this is our K, which is order 1 upon epsilon square or 10 upon epsilon square. And this is T, which is order log 1 by delta, right? So this gives us one estimate. This gives us another estimate. This row gives us another estimate. So all the T estimates we get, we just report their median. This median is our T estimates. And that has the guarantee that the error, the difference between our estimate and the ground truth quantity will be more than this. This will be at most delta, right? So any doubt on this part? Okay, so I'll just quickly wrap up by stating the space required to store the sketch. Right? So the space complexity so it consists of two parts. First is space to store this array of size T into K. And the second thing is space to store hash functions. So how much space do we require here? So it's Tk order 1 by epsilon square into log 1 by delta. So this many counters do we need? But we need to store some values in the counter as well. And that are essentially the frequency of basically some of the frequency of some elements in the data stream. So, right. So to store, basically we have this many counters, T into K many counters, but each counters store some value, right? And how much space we require to store that value? So is this part clear? For example, in this cell, what is the number that we may have to store? could be as big as size of stream, right? Which is M, right? So any counter could be as big as, could store a number which is as big as size of the stream. So to store the, basically it may have to store like a number which is as big as M. To store that, we require log M bits, right? So this is the space to require to store this two-dimensional array, and space to store hash function. So basically we require t copies of pair of hash function G and H. So we require order T, and to store hash function G and H, we require log n bits, which is order log 1 over delta to log of n. So overall it is order 1 by epsilon square log 1 by delta log m plus log n. Okay, so any doubt on whatever we have covered so far?
So that log of 1 by delta, can you explain once again?
Log 1 by delta.
Just
Okay.
above.
Yeah, this part. So suppose if we have some algorithm in which we are getting this sort of guarantee, right? So this is, in a way, this is kind of bad event, and its probability is upper bounded by, say, 1 by 10. But suppose we are not happy with 1 by 10, we want this to be as close to 0 as possible, maybe close to some delta where delta can take value maybe 10 raised to the power minus 5, right? To boost this thing, what we do, we just repeat the same thing again, log 1 upon delta times, right? So basically repeat t times, where t is order log 1 upon delta. We'll get t estimators, and we'll take medians of those estimators. Then basically we get this guarantee. So I'm not giving proof of median trick, which is the statement of median trick is that, like, suppose we have any algorithm in which the probability of error is at most, say, some constant, then we can, by repeating the same algorithm t times, where t is order log 1 by delta, and taking the medians of the corresponding estimator and reporting that thing as a final result, we can boost the probability of error to sufficiently close to basically we can bound the probability of error to be delta, where delta is sufficiently close to 0. And its proof is via like using Chernoff. So I'll not go over the proof, but you can just assume that this is true. And the same thing we did over here. So this is if we use one sketch, and then what we did, we repeat the same thing t times, where t is order log 1 by delta, right? And each of them give us one estimator, and we use the median of those t estimators. Then using this the guarantee of median trick, we get this guarantee. And then rest we did the space and time, space analysis. Okay.
And this delta is also user provided, right?
So basically epsilon and delta is provided by the user. Okay, so basically users give you suppose user asks you, basically come up with some sketching algorithm which in which the error in the accuracy is this much, and the error in the confidence is this much. Then basically you can, using the value of epsilon and delta, you can design a two-dimensional sketch and use these hash functions H and G appropriately. Okay, so typically in streaming algorithm, our aim is to come up with epsilon delta approximation algorithm. So I'll just write the guarantee, basically the statement of epsilon delta approximation, and then we'll stop. So I'll just, for sake of completeness, I'll write. Okay, so okay, so suppose A sigma denote the output of a randomized streaming algorithm, and this, note that this a sigma is a random variable. And let phi of sigma is the optimal answer. And we say that algorithm A gives epsilon delta approximation of phi if basically probability that the value that our algorithm is outputting and the ground truth is more than epsilon is delta. This is called additive approximation. And probability that A sigma minus phi sigma is more than epsilon times phi sigma. It's at most delta. So this is called multiplicative approximation. Right. So this is typically the setting of epsilon delta approximation. So in streaming algorithm, whatever algorithm we have seen so far, our aim is to come up with epsilon delta approximation. Basically, error in the accuracy is determined by the parameter epsilon, and error in the confidence is determined by the parameter delta. And this epsilon and delta can be sufficiently close to 0. Right, and you can think of that they are provided by the user. All right. Okay, so I'll stop here now. So it's, I think, 10:35, 34. So we'll meet at, sorry, 11:34. So we'll meet at after 15 minutes, 11:50 sharp. Okay.
So one question I have.
Yeah, sure.
So this space complexity, whatever you have shown, it is almost similar to the other streaming algorithms also. Like I'm a little bit confused. Like most of the algorithms are coming with this almost similar kind of derivation,
Yes.
and also similar space complexity, like Morris counter, which we have been taught last, and then like some of this probabilistic algorithms are coming up with exactly the same complexity.
Yes. Yeah, you are right. So technique wise, they are slightly different, but the space complexity, most of them are something like this, basically logarithmic in the size of stream and the size of universe, and this sort of dependency on epsilon and delta. But they're final space complexity is somewhat similar to this thing, but the way we designed the algorithm, they are somewhat
Correct.
different. So that
Yeah,
is depending on the problem statement, but the space complexity is something of that sort. And essentially, this is the holy grail of streaming algorithm, to come up with algorithm whose space complexity is logarithmic in n and m. Right?
okay, got it.
Okay, so we'll stop here now and we'll meet at 11:50.